continuing my discussion of calculating important, crucial interfacial mechanical properties in ordered fluids using this new approach called the Kahn-Hoffman vector, capillary vector, which is just the vector that gives you 1,3 and 2,3 stresses and give you proper information of contact line angles as a function of anchoring. So this is, and now we're moving forward. The original plan is how to derive a robust, well-formulated shape equation for pneumatic liquid crystal. So this is how a liquid crystal deforms and interacts with the bulk. So what's the proper formulation? So we already know what's Laplace equation, everybody knows. Delta P equal to gamma H, where H is the average curvature. So the key work here is when you put liquid crystal physics, what happens to Laplace equation, right? So with this is the basic equation of normal force balance equation at an interface. This is what we introduced before, is the bulk, the jump in bulk stresses. So this is projected along the unit normal. So this is the difference between two pressures. And this is balanced by the so-called capillary pressure, which is the surface divergence of the surface stress tensor projected along the unit normal. So if you want to plug in the components of the stress tensor in this equation, you have difficulties in the fact that the stress tensor has a basis. And when you took derivatives of the basis, it gets very complicated. So this approach we developed, is a very clean, elegant way to avoid this problem. So to avoid this problem, you introduce the capillary vector and find the proper projection between vectors and tensor. So the capillary vector gives you the stress tensor when it's projected with this third order asymmetric projector operator. So once you have this projector operator right here, and up to the so-called Ericsson stress is a distortion stress due to derivatives. But the key point is you have this term here, you plug it in right here, and you find out this amazing result, that the capillary pressure is just the divergence of this Kahn-Hoffman vector, X, capital X. So you went from a very complicated surface divergence of a stress tensor, a very complicated, messy thing, to something anybody can do, which is the divergence of a vector. So the divergence of this vector, now that's the nice, clean, beautiful result, that this vector is a function of Q, K, and grad Q. So the only thing you have to do is take the divergence of this guy. That's the capillary pressure. And the divergence, according to definition, is you expand it in terms of all the variables it depends on. Right? This kind of thing. I put an S, an S, an S. Sorry. Okay, just expand it. This part is the geometric part, right? I'm a little messy. I'm messing up this is a scalar, so the number of dots here is a little messed up, but doesn't matter. The whole point I want to convey is the capillary pressure is just the surface divergence of this vector. And this vector it contains geometric information. This B is just the curvature vector. So you expand it in all the variables you have in the system, and now you can see where the geometry comes in and where the Q tensor come in. It's two different bins. One bin is the geometry bin that should contain the Laplace pressure, and the other bin is what contains the Q tensor information. So once you do that step, you find this result. So this is the geometric part, and this is the Q tensor part. So this geometric part contains Laplace pressure. So this term here, this times this, is Laplace pressure. This term, the second derivative, is called the Herring's pressure, what you see in the textbooks. Second derivative appears normally in this pressure, capillary pressure due to curvature. And then this part is due to the fact that you have a Q tensor floating around. So now you clean up the left-hand side. This was a jump in normal stresses. And when you clean up the left-hand side, you put delta P there. So you have the long-range elasticity of a pneumatic. Then you have the geometric component of the capillary pressure. And then you have the Q tensor component of the capillary pressure. Very clean and beautiful formula, and each term has a physical significance. This term introduces pressure due to long-range elasticity gradients in the pneumatic in a tactoid. This term here is the Herring's term that turns to remove sphericity from the system, doesn't care about minimum surface. This term cares about tilting. This is a tilting term. And here you have all the gradient terms from Q tensor. As indicated here, you might have a drop. Parts of the drop are tangential, parts of the drop are perpendicular orientation. So,
you are using the X code.
That's better.
The tensor IS is the surface identity tensor. How is this defined?
Yes.
I minus N K
Yeah.
also?
I S is I minus KK.
Okay.
Yeah. So yeah, when you derive these derivatives is messy. I think that's what you ask when you want to write something like this. Right, or yeah. So this thing, what really is this, right? And then when you see it written like this, the second derivative, you have to take the derivative of this. That's the derivative of that with respect to k. And this is a k embedded in here. So you have to be very careful when if you write something like this, shorthand is nice and pretty, but you have to take this whole thing, and there is a k here.
Where from comes this dxs over dq?
Here?
Yeah. Yeah, well, and another one.
Here?
Yeah.
Because we say that this was the whole point. This you take the divergence of this. This vector here is the capillary vector.
Yeah. This I see, but how you compute this dx over dq? How do you compute it?
This?
Yeah.
This is, I already have xx parallel, that's xs parallel is minus is dotted with this f, this k. Right? And this gentleman here can be a function of Q, K, and in some case, if you have L to 4 and other things like that, surface gradient of Q.
So, but it still contains geometry because
Yeah, you take it, yeah. When you take the derivative with respect to K, and you have explicit K. Yeah. We can go over later the notes. The key point is, so in this more generic formulation, so that was, this is the most general equation you can write for a liquid crystal, the most generic. So you have long range elasticity, here you have the Laplace pressure, here you have anchoring, here if you have a system that supports surface Ericsson stresses, and here you have the gradient of Q tensor information. Things like, for example, here you have anchoring, for example, for sure, and here, if you have L24 terms, you have these terms. These terms, you can see are important, non-negligible when you have things that have gradients along the surface. So the first term, so Laplace pressure, so I want to show Gulf plot, which is a polar plot. Gulf plot is the polar plot of the interfacial energy up to a scale, a number, and the shape, if you don't have any shocks, so you have a smooth shape, and that smooth shape should correspond, the shape of the drop should correspond to the polar plot of the free energy. So this is the Landau-Degen model. This is a liquid crystal drop growing at 25 degrees Celsius. This is the surface energy as a function of the angular coordinate, where the angular coordinate is defined is you moving around, right? And at some point, this is a variable, n dot k. You don't know what n dot k is. It's an angle that might vary. So plugging this, computing the interfacial tension along the circle, this is the magnitude, right? So you get a figure like this. And then we compare that figure with the shape of a drop. Of course, we normalize it to the same size, and you can see that at this, for this temperature quench and at this stage, you have a non-spherical shape that is well captured by the anchoring energy that appears, which is responsible for a contribution between the director and the unit normal. So that's the interfacial free energy that depends on N and K, so-called anchoring. This term here, this example here shows an example where these Q pressure, Q tensor terms play an important part in shape and structure determination. So this penalizes this kind of situation. As I mentioned earlier, when you have defect nucleation, it's because you have frustration. What is the frustration? Here is biaxial orientation because the director is planar. Here you have uniaxial orientation because the director is along the unit normal. So here you have frustration. The way to relieve frustration is to nucleate topological defects, and this is what, so these are patches of biaxial interface in a sea of uniaxial orientation. And so these are two-dimensional simulations of a nematic drop growing isotropic phase. You see all the nucleation of topological defects. They are of strength plus 1/2. They decorate the main diagonals. So the whole point with these simulations is to show that you get defect nucleation not only for this three-dimensional Kibble mechanism where drops impinge from a phase transition. This is the typical scenario called Kibble, right? So when drops impinge, you get a topological defect due to frustration of the orientation, misorientation between domains. So this is a multi-droplet scenario of creation of topological defects. This is a single drop scenario of creation of topological defects. And the origin comes from frustration on an interface because the selection of orientation is random. It's not, well, it obeys different forces. Here you have uniaxial, here you have biaxial. So the other interesting point about the beauty and use of this capillary vector is to study Rayleigh-Herring's instabilities. So with this simple vector, you can get a lot of mileage, clean view. So you compute the capillary pressure in a cylinder, a pneumatic cylinder, and you have at least these three terms. Now, instead of working with Q tensor, I work with a director. So you have an area stretching term, like Laplace term. You have an area tilting term. This is perpendicular component of the vector. This is parallel component. And then you have director tilting. And when you do the analysis, you linearize the system and say the capillary pressure is a critical value equal to 0, you have the Rayleigh instability. You clean all these liquid crystal effects. You recover a linear thresholds of Rayleigh. And when you leave them, you recover or expand the palette of instabilities, because now the instability is not governed by area minimization as in Rayleigh. You have area tilting. So this is the initial area, this is the final area, this is your perturbation, this is the initial radius of your fiber, these are the longitudinal wave vectors, these are the azimuthal wave vector m squared. So when m is different than 0, the final area is bigger than the initial area, because you're adding m squared. So m bigger, different than 0 are chiral modes. So what you end up with is according to the different initial orientation, whether you have onions, when you have axial, whether you have splay. So you have a big story. I don't have time to give you a total stories in this paper, 2004 or 2002 with I. John. So this is peristaltic mode, M0 by Rayleigh. These are chiral modes where M is different than 0. And the key is gleaned out of these terms. Although the area increases, you have decrease of energy by changing the shape. And the shape can change by creating chirality.
So this FS term?
Huh?
FS.
Yeah.
Remind me how does
That's the surface free energy.
Okay.
Yeah.
Depends on K.
Yeah. So that guy, Fs is Fs isotropic plus, let's say, this director model, and K square plus, other terms that like L24 type of terms. So this is the anchoring part. So you have, when you take the derivative of this guy with respect to K, you get X parallel here. And this X parallel then is a function of N. And this is what I was trying to convey, that in this kind of problems, you have to think about solving these problems. You have an orientation and a shape. And so these two things can be hard or soft. So whenever the shape is soft, it's going to change the shape. The orientation changes the shape. And when it's hard, it's the reverse. The shape changes the orientation. So these modes tell you that you can change the shape also with the director through the anchoring. So lastly, yeah.
I'm trying to imagine how, I guess when you plot the previous,
Yeah.
When you plot these cylinders with the ridges on them and so forth,
Yeah.
you're solving a linearized problem.
Linearized, yeah.
Yeah. So what kind of a problem is that? Is it
You can generalize. I'm sure this is a kind of virgin field we can do in the future, nonlinear. We only touched. The key point was this, as I mentioned before. If you look at the literature, even the classical literature by Levitch, for example, physicochemical hydrodynamics, you have chiral modes on fibers. He says, look at figure 0.7 and then goes on to something else. So this been reported is possible. The only thing you need is a medium, a material that has anisotropy. So lastly is thermodynamics. So now I want to put mechanics and thermodynamics together. Mechanics and thermodynamics together, insist on some words about thermodynamics. So you start with the Euler surface equation that tells you that internal energy is equal to the entropic part, the absorption part, and now you have the interfacial tension. I went from, I just call it gamma. Fs, what I had before Fs, I call it gamma. I'm putting together different papers together. The whole point is that this gamma is a function of at least Q tensor and the unit normal through anchoring. So you take the derivative of the surface Euler equation with respect to Q. So you do this derivation, and then you use the Maxwell relations to express derivatives, and you do a little bit of algebra, and then you end up with all these derivatives of the Q tensor with respect to temperature, with the Q tensor with respect to the chemical potential of the J component. And here you have the derivative of the internal energy with respect to the Q tensor. And this tensorial is just a tensorial generalization of the anchoring energy. And here you took the derivative of this with respect to Q. So here you have the derivative of this, I put a minus sign there, with respect to Q. Therefore, at equilibrium, d gamma dq is 0, right? And this equilibrium is called the easy axis. Well, it's not, I should say, what is the orientation and structure of Q that minimizes the interfacial energy? Is d gamma dq equal to 0. So when that happens, you reach the lowest energy level. Then if this is 0, this whole thing is 0. That's the thermodynamic content of anchoring. Yes?
You've written G as the derivative of the surface tension, gamma,
Yeah.
with respect to Q, and Q is a bulk quantity.
Evaluated at the surface.
But how close to the surface?
In this formulation is continuous level is at the surface. I didn't put, whenever you discuss anchoring, you say what is the anchoring is a local quantity, and you say what is the state of my interface in terms of orientation, the one that minimizes the anisotropic content of the interfacial tension.
Because if I think about writing down the free energy of the system,
I think if you can simulate this or do it in a kind of you put in your coordinate system in terms of layer and do a smooth, we have done that. So the point of this is that is lost in the literature is that whenever people do an experiment and they see a transition like this from planar to homeotropic, they say, well, it's better energy, it's energetically favorable to tumble or something. But the key of the story, as we see in a minute, is that all these remaining thermodynamic terms, they have to balance each other. The energy plus the entropy plus the absorption terms have to balance each other and give you 0.
I mean, sorry, the reason that
Yeah.
I'm asking this
Yeah.
is that if I look at the physical contribution
Yeah.
to the interfacial tension,
Yeah.
it of course includes the interactions between whatever's on the surface
Yeah.
and the molecules in the bulk.
Yeah.
And generally, there are many interactions, including dispersive
Yeah.
long-range interactions.
But this is, I know, this is not what you see, this is the concept. What is the easy access?
Yeah.
What is Gedanken? What is the state of this Q tensor that minimizes the free surface. Then, if you want to solve a problem, you go back to your mechanics.
Yeah.
What? And you solve the whole shebang. And this equation then is coupled to the nematostatics equation in the bulk. And the kissing terms are here, because this depends on the Q tensor. Evaluate the bulk Q tensor evaluated on the surface.
That's an assumption.
Yeah. And and this, therefore, this simple thermodynamics tells you, in principle, that you can change the Q tensor with temperature, so you can have thermal transition of orientation, as I described on Monday. This example, homeotropic to tilted anchoring. These were experiments in terms of contact angle as a function of temperature of a cyanobiphenyl on a polymer surface. At 45 degrees, you have this contact angle sharp transition, and that was due to homeotropic to tilted anchoring changes. Here, these are Abbott experiments with surfactants. You do a planar to homeotropic transition, activating this absorption term. So we have absorption mechanism and thermal mechanism to change orientation at a fixed shape. Shape doesn't change. So the next step is there is something similar to this concept, prefer shape. And these are beautiful experiments. I don't have to do a lot of talking. I let the experimental work talk for me. So this is 5CB, a cyanobiphenyl in water. So these are dispersions of liquid crystal drops in water. And then you add some surfactant, that's C-tab, in there. There is a Kraft point as a function of temperature where you have micelle formation. At high temperatures, at around whatever 20-something degrees, the micelles are stable. At lower temperatures, the micelles are not stable in the bulk, and you have preferential absorption. So at lower temperatures, where you have more surfactant at the interface, you have lower interfacial energy, and you should see things happened. So what happened? Drops becomes filaments. So you have a drop to filament transition driven by this combined action between temperature and lower of the interfacial tension. Right? So this is the length of these filaments. They've done this beautiful work by Blanc, published in Physical Chemistry B, 2008. It's a short paper. So here is what you have by equilibrium close to this transition temperature at the Kraft point, where you have filaments and you have drops. And this is the length of the filament that increases as you lower the temperature. And this shows reversibility of this effect. Higher temperature, short; lower temperature, more surfactant, longer. So how you explain this using the same thing I'm talking about? So surface thermodynamics, so the Euler equation. So this was a revealing also abstract here, so quoted by Blanc, who is an expert in these kind of problems. Other induced effects have been poorly explored. Using, these surfactants, we demonstrate large shape transformations that can be achieved in direct liquid crystal water emulsions. Large shape change. So if you plug it in here, so what is the trick here? This is the Euler equation. You take the derivative now of the Euler equation with respect to the unit normal. You want to describe shape change. Before we took the derivative with respect to Q. Now we take the derivative with respect to K, and after that you take the surface digradient of the whole thing. And this term now here plays the role of d gamma dq. So before we have d gamma dq equal to 0. That gives you the easy orientation. This term here is d gamma, dx dk equal to 0. That gives you is this term here. So how do I get that? I take the derivative with respect to k, and then I take the gradient, the divergence of everything. So this term here plays the same role as easy shape. So for any kind of system, chemical system, liquid crystal, water, surfactant, at a given temperature, I have a preferred shape. And that shape will change with temperature and surfactant concentration. And this is what this tells you. The unit normal, again, doing a little Maxwell derivatives, you find that the unit normal can be changed with temperature, the unit normal can be changed with chemical potential. And so this term then explains nicely the effect observed. Yes, Jimmy?
Yeah, this is just a matter of the bulk distortional energy overwhelming the surface energy because you have reduced the surface tension?
Well, okay, so you have reduced interfacial tension, but so you could have other phenomena like the bulk, the drop can be increased in shape. The drop can be increased in volume or something, or change in volume by associating with others. So what we show here is a single shape easily changed by the temperature, which changes the interfacial tension into a rod. So if you put a liquid drop of whatever, water in oil, you're not going to see this.
Why would the thread be serpentine?
Yeah.
If as dictated by bulk energy, as it seems to be, I would expect a very straight rod.
So these rods, of course, they're swimming in this. They have thermal fluctuation. They have bending elasticity and torsion elasticity of certain magnitude. So depending on how you prepare the system, like disclinations, as you can see easily in a pneumatic system, which is the inverse object, can easily bend and twist. So there, the modulus of bending elasticity scales with the Frank constant. All right. So lastly, we're talking about thermodynamics, and we're talking about where we're going with all this. So in this example here, the last example of the theoretical components. So here we study a system that has 3 order parameters. 1 conserved order parameter, which is concentration, and 2 non-conserved order parameters. So here we put, this is experimental work. Reven is a chemist at McGill. So these are gold nanoparticles treated by her so that they disperse nicely into a pneumatic liquid crystal like 5 Cb. And we have the system. This is our thermodynamic phase diagram. It hasn't been validated yet, but some parts have been validated. It's a complex phase diagram. The key point is you have a large region here where you have pneumatic in equilibrium with crystal pneumatic. So this is the pneumatic. So you have orientational fluid and randomly dispersed nanodrops. Here you have an orientational order pneumatic with a positionally ordered nano lattice. Okay? So we solve all these 3 order parameters, and these are typical structures that appear highly non-spherical. And in addition, what is very exciting here is, we have small miscibility of nanoparticles in the liquid crystal phase. Therefore, the nanoparticles are expelled from a pneumatic drop. They're expelled. So, of course, the pneumatic drop is anisotropic. The expulsion, the mass transfer towards the interface is anisotropic. Quickly, you got dendritic structures. And here, we move in this part of the phase diagram where you have this scenario. You have a large concentration of nanoparticles decorating the interface, and here you have crystallization of nanoparticles in a beautiful dendritic format, and this is our adaptive mesh approach. When you solve 3 order parameters, multi-scale problem, but adaptive mesh works very well. And you can see the phase diagrams of this system is I know it's complicated, but the key point is you have two important lines when you mix a liquid crystal with nanoparticles, right? So you have temperature, you have concentration. So what happens? Here you have pure liquid crystal, pure LC. So you add in nanoparticles, so you have a lyotropic system. The isotropic nematic temperature decreases. And that's this dashed line. And because you have interaction, miscibility, entropy, this line splits into two. That's these lines here. And here you have the nanoparticle crystallization line that we all know, excluded volume, Carnahan, Stirling, etc. So that's the vertical line here. And so you have other mixing effects, and this line splits into two. So that's the bottom line of thermodynamics of this complex liquid crystal nanoparticle. Depending on the interaction, then you're going to have complexity. This phase here is some kind of spinodal II curves. Okay, so how am I doing on time? 2 minutes? Eh? Well, how much?
5 more.
Okay, so I don't have much time talking about what I wanted to say, but so these are all the examples are in that review paper I mentioned earlier. So for films, so I'm interested in describing what happens when you have nematic films. So this is the process, it's a drag out problem. So you have a polymer fiber, radius R in the micron range. This is a liquid crystalline bath, like 5 CB. You can control the temperature, increase or decrease. You drag this fiber, you entrain a certain amount of liquid H. H is the thickness of your coating, and then the classical fluid mechanics is the Landau-Levitch-Deryaguin coating scaling law that tells you that this film thickness divided by the radius of the fiber scales with the capillary number to the 2/3, where the capillary number is viscosity, velocity of the fiber divided by interfacial tension to the 2/3. And this is what my colleagues at Georgia Tech find in the isotropic phase. They have 2/3 scaling. H over R is scales with B to the 2/3, as indicated here, the experimental data. And then when the lower the temperature, the optic axis emerges, the scaling is capillary number to the first power. So I'm not going to go through this. Ian give 2 lectures on Leslie Erickson theory. So the key of this point is demonstrate what does anisotropy does to interfacial capillary problems. So the key concept I want to get across is for anisotropic systems, there is no one-to-one correspondence between the type of stress and the type of deformation rate. So here we have shear rate, extension rate. On this column we have the stresses. So this tells you that a shear deformation gives rise to shear and normal stress, and an extensional deformation gives rise to shear and normal stresses. And this is kind of trivial for anisotropic systems, since the viscosities and these torque coefficients are tensorial quantities. So from here, if we want to compute extensional stresses, we put I equal to J. And if we want to compute shear stresses, we put XY. So we quickly see that for this kind of fluids, the normal stress difference, which is TXX and minus TYY, obtained from here, gives rise to, first of all, there is a strong dependence on shear rate, linear dependence, but it has a lot of sign changes. So it's not zero. It's never zero. And secondly, if you just consider shear flow, the first normal stress difference divided by the shear rate is a constant at sufficiently high flow rates. These are Conan plate experiments where we plot this ratio, and these are experiments and simulations, clearly see that N over Tx, the normal stress, divided by the shear stress in a simple shear flow experiment is not 0 for liquid crystals. So we now go to the textbooks, really, and find the film formation model, which is a ratio, a balance between shear forces and normal stress forces. The balance of this is balanced by the capillary force. So for these systems, I use the Leslie Erickson, compute shear stresses, and compute the normal stress. And this is the key point. The key point, if you look at the hydrodynamics of this problem for a complex fluid, first you have these two things. Shear can give rise to extension and shear stresses, and extensional rate can give rise to shear and normal stresses. So it's a 2 by 2 couple matrix. So this flow is not a simple shear flow because the cross-section decreases. So at the end of the day, you can compute the shear stress you have to plug in here and there, and the normal stress that you plug in here. So we do that, and you have things like V is the characteristic velocity of the fiber, lambda is the characteristic length that is associated with stretching, and H is the characteristic distance associated with shear. So we plug these shear normal stresses into the film formation model. We do some scaling analysis, and we clearly find the most general law that generalizes the Landau-Levitch, the Ryagin coating law, and is expressed in terms of a capillary number, H over R to 3/2, divided by this polynomial that contains all the complex rheology of the fluid. If I have a Newtonian fluid, I have only alpha 2, and alpha 2 gives me the 2/3 scaling. If I have a complex fluid, the most important term is the first term, that is proportional to HR to the 1/2. And so 145 term, this term, gives you capillary number to the first. And the alpha 2 term for Newtonian fluids give you this LLD scaling. And that's the bottom line. I wanted to talk a little bit about spiders and carbon fibers. They both spin liquid crystals. The spider does it with a polymer solution. As indicated here, this is the manufacturing of the polymer solution. This is a protein, it's soluble in water. You spin it, you go through a spinning duct, a spinneret, and you have phase separation and crystallization. You get a beta sheet crystal, right? Ultra strong. And all what you can get from liquid crystal physics, this is the duct of a spider, and this is the so-called scape texture, and this is the point defect texture of plus, minus, plus, minus. So you have scape to point defect. This is the actual size for silkworm and spiders, and in both spiders and silkworms, you get the same texture transition. You go from a scape texture, as indicated here, to a point defect texture. This is radial hyperbolic, radial hyperbolic. So you go to same texture transition before you manufacture the super strong fiber, and this is what is predicted by liquid crystal physics, where here we plot the concentration decreases going up, and here is the radius of your capillary. And this is what happens in a spider duct. Here is a large radius, and then the radius, you have a double hyperbolic reduction, so you move from right to left. Large scale capillary gives you scape radial. Small capillary gives you this point defect as predicted by liquid crystal physics. So this is the beginning of a new area of interfacial physics of complex fluids, and I have to quit. I have the chairman here. Thank you.
So we have time for one short question.
Okay.
The Landau-Levitch problem, scaling,
Yeah.
I didn't follow it very well. So H over R is small, right?
Yeah.
Then wouldn't the denominator still be dominated by the Newtonian viscosity? Why would you take the 1/2?
Well, here is one term compared to the other is significantly different. As you can see that H145 term is dominant. The first term dominates, even to the plain Newtonian viscosity. So the rheology is in the bottom, right? I know H over R is not 0. You know, H is micron range. You know, it's not 0. So
H over R is small, right?
H over R, yeah, but it's not negligible.
Right. For that term to win out against the Newtonian viscosity,
Yeah.
you have to rely on the coefficient to be very large.
If you see, you know, scaling capillary to the first power, so if that term is the dominant term, and the A2, the Newtonian term, is negligible with respect to the complex fluid viscosity term. You know, so there are 2 points here. One is when you have non-Newtonian flow, polymer flows, even if it can appear to be a shear flow, you can have extensional components. So is the extension component of this coating flow negligible for a complex fluid? And the answer, this kind of scaling is also observed in polymer solutions. Okay, so it's observed in other complex fluids, capillary to the first power. So here we have capillary to the first power, and is in our approach, of course, is due to normal stress N1, and also is due to the fact that you have extensional deformation. Yeah, when I go to the it's beautiful experiment. When I go to the isotropic phase, I kill any kind of kinematics and kill any kind of complex fluid, and I rest capillary to the 2/3. And this scaling we show here, it has the most general scaling for any complex fluid, because it has normal stress and it has extensional kinematics.
Oh, I think
Okay.
we can go for the G.
Yeah.
We resume at 3, right? We are going to continue at 3 o'clock. All right. Let's thank the speaker again.